Welcome to the Explainer. Okay, today we're diving into something that feels, honestly, pretty magical in the world of digital logic. Have you ever wondered how engineers can be absolutely certain a complex microchip actually works before they spend millions of dollars physically manufacturing it? Well, the secret is pure software. They simulate the hardware using a highly specialized testing environment. So today, we're going to break down exactly how that's done by exploring how test bench code simulates hardware.
Okay, let's dive into this. Here's our roadmap for today. We'll start with what is a test bench. Second, we'll look at setting up the tools. Third, the anatomy of test bench code. Fourth, simulating the adder. And finally, simulating sequential circuits. Even though we're dealing with dense code and tools, I promise this roadmap will make everything super clear. Section 1. What is a test bench? Entering the virtual lab. Before we look at any actual code, we really need to wrap our heads around what a test bench is. Think of it as a virtual lab environment, or maybe even better, a puppet master. You see, this environment has absolutely no physical inputs or outputs of its own. Its entire existence is simply to wrap around the design we want to test. So technically speaking, a test bench is a specific style of Verilog code used to instantiate a module so it can be simulated. It's written entirely to specify exact values for a module's inputs at very precise simulation times. It essentially just plugs right into our target design, feeds it highly controlled signals, and watches how it reacts. Now, you might be wondering about that target design we're testing. We call that the DUT, or Design Under Test. In our explainer today, the main DUT we'll look at first is a multi-bit adder called addern. The DUT is the actual puzzle we're testing inside our virtual lab environment. And what's cool is this test bench module can actually be saved right inside the exact same .v file as the addern design itself. Section 2. Setting up the tools, preparing the software. Now, before we can start writing code to test our DUT, we just have to quickly make sure our software environment is configured to bridge the code and the actual simulation software. We're going to be using Intel's Quartus software to manage our project and a tool called Questa to run the simulation. To get them talking to each other, we use NativeLink, which basically lets us launch Questa straight from Quartus. The workflow is actually beautifully simple. In Quartus, you just go to your EDA tool options and punch in the file path for Questa. Next, under Simulation Settings, you tell Quartus to use Questa. And finally, and this is absolutely crucial, under the NativeLink settings, you select Compile Test Bench. Clicking that opens the new Test Bench settings window. Right here, we have to specify two really important things: the test bench name, which we're just calling adder_testbench, and the top-level module in that test bench, which is our DUT, adder. This is exactly how the software properly links our virtual lab to the specific circuit we want to test. Once those are locked in, our software is fully prepped and ready to go. Section 3. Anatomy of test bench code. Deconstructing the adder. Okay, with the tools ready, I want to take you on a quick guided tour of the actual Verilog code itself, because this is where we write the literal instructions for our simulation. Now, what's really interesting here is how logically the code flows to create this testing environment. This is the complete test bench for our multi-bit adder. Notice near the top, the module adder_testbench is declared with empty parentheses. It has no inputs or outputs of its own. It's completely self-contained. So let's break this down, almost like we're translating it, to understand how it controls the simulation. It all starts at the very beginning. Line 1 is a compiler directive setting the timescale. The first part, 1 nanosecond, sets the base unit of simulation time. The second part, 1 picosecond, sets the resolution. This is incredibly important because it specifies the exact granularity of time for which the simulator will evaluate signal values. It's essentially setting up the master clock of our entire virtual universe. Next up, we declare our signals. And we have two distinct types here, reg and wire. It's vital to contrast these two because they do completely different things. Signals declared as reg, which is short for register, act as our input controllers. We use reg for our inputs because they can be assigned a specific value in the code, and they literally hold on to that value until we explicitly tell them to change. On the flip side, wire signals act as our output monitors. They connect directly to the outputs of the DUT, just to read and carry the results generated by the hardware design. Moving down, we instantiate the actual DUT, plugging it in, and then we hit the initial block. This block is basically the master script for our sequence of events. It kicks off at time 0. First, it assigns starting values to our reg input signals, setting x, y, and sin to 0. But check out what happens next. You see that hashtag 20? That hashtag 20 is a delay command. It tells the simulator, hey, wait exactly 20 simulation time units, which we already know is 20 nanoseconds, before executing the next line. So right at 20 nanoseconds, input Y changes to 10 in decimal. Then it waits another 20 nanoseconds, changes X to 10, and so on. We are injecting specific stimuli into our adder exactly when we want them. Section 4. Simulating the adder. Visualizing the results. We've written the script, and now it's time for the payoff. By running the RTL simulation from the Quartus menu, we launch Questa. We pull our inputs and outputs into the wave window, set our zoom, hit run, and boom, we get visual proof of our code. And here is what that visual proof actually looks like. The top view shows the redex or base numbering system set to decimal. The bottom shows the exact same simulation but set to hexadecimal. Notice how at exactly 20 nanoseconds, the Y signal jumps to 10 in the decimal view, just like we scripted in the initial block, and at 40 nanoseconds, X joins it at 10, which brings our output sum perfectly to 20. Viewing these waveforms in different formats, like A and 14 and hex, makes it so much easier for engineers to verify the logic and know for sure the multi-bit adder is performing flawless math over time. Section 5. Simulating sequential circuits. Introducing time. Let's move on and see how this builds into something even more complex. You see, the adder we just tested was a combinational circuit. Its output depends only on whatever its current inputs are. But what about sequential circuits, where the outputs actually depend on time and a whole history of previous states? Take a look at this schematic of an accumulator circuit that uses a down counter. Notice the clock input driving both the register and the down counter. This introduces a physical loop, meaning this circuit relies on a continuous, pulsing heartbeat to function properly. The entire purpose of this accumulator circuit is to add the values of input X for every single clock cycle, just continuing to accumulate that sum until the down counter hits 0. Simulating this requires way more than just pushing static numbers at specific times. We now have to simulate an ongoing, perfectly timed clock signal right inside our test bench. So here's the test bench code for our new accumulator DUT. Because this circuit relies so heavily on time, we have to give an initial starting value for our clock signal, clock 50, setting it to 0 in the initial block. We're also using a series of switches to feed data to the X and Y inputs over time. But honestly, the real star of this test bench is this single line of code right here. Always hashtag 10, clock 50, less than or equal to, negation clock 50. This is an always block. Unlike the initial block that just runs once, this block loops continuously. It's essentially saying, wait 10 nanoseconds, then invert the current state of the clock 50 signal. By constantly flipping the signal from 0 to 1 and back every 10 nanoseconds, we are generating a perfectly periodic 50 megahertz clock waveform entirely in software. It's brilliant. And this brilliantly illustrates the whole thing coming together. In this 300 nanosecond waveform, you can clearly see that pulsing 50 megahertz clock signal ticking away at the top. Let's trace our script. At 20 nanoseconds, our Y input is set to 10. That tells the accumulator to run for exactly 10 clock cycles. Then, at the 40 nanosecond mark, our X input is set to 30. Look down at the bottom waveform for the sum output. Starting right at 40 nanoseconds, the number 30 is perfectly self-added on every single clock cycle. 30, 60, 90, all the way up to 300 across exactly 10 cycles. The simulation works absolutely flawlessly. What we've really seen today is the incredible power of test benches to bridge the gap between logical intent and physical hardware. By instantiating a DUT, defining timescales, driving inputs with registers, and simulating dynamic clock pulses, we can perfectly predict hardware behavior before it even exists. Which leaves us with a pretty fascinating question to ponder. As our testing software becomes ever more capable, mapping millions of microscopic electronic interactions down to the picosecond, if we can simulate time and logic perfectly in code, where does the virtual lab end and physical reality begin? Think about that the next time you use a device powered by one of these brilliantly tested chips. Thank you so much for joining me for this explainer, and keep learning.